Hello everyone, today I'm going to be walking you through a PyReason advanced tutorial. All the code shown in this video will be linked in the description below, as well as a link to our full GitHub, which has more documentation and other examples. So let's get into it. So first off, I want to start with a disclaimer that this tutorial builds a little bit from our pet store PyReason tutorial, which is a slightly simpler version or example using PyReason with a lot of the same ideas. But this tutorial is going to take a graph of customers, their cars, pets, and relationships, and then use PyReason to create rules and facts that will interpret and label the different characteristics and relationships in the graph. So let's get started. So, brief overview of what we are going to do today. We're going to first create a graph in Network X, then add rules and facts in PyReason, then run PyReason, and then trace and read our explainable output from PyReason's explainable reasoning process. So let's get started. All right, first and foremost, we need to create a graph. So I'm going to be manually creating a graph using Network X. You can also load in a graph in the form of a GraphML file, but we're going to be making our own graph today. So first, we're going to add in the node data. So the node data for this example are the different customers. So we have John, Mary, Justin, etc. The pet details, dog, cat, rabbit, etc. And then car details, so different types of cars and their colors. So that's our node data. And then we're also going to have edge data. So our edge data is going to be the relationships between the nodes. So the first type of relationship we're going to have is a friendship. So this is a directed graph. So customer 2 is friends with customer 1, customer 0 is friends with customer 1, so on and so forth. The next relationship we're going to have is car ownership. So customer 1 owns car 0, customer 2 owns car 1, so on and so forth. And then the final type of relationship is a pet ownership. So customer 1 owns pet 1, customer 2 owns pet 2, so on and so forth. So let's take a look at what this looks like first so now we've added our data. Now we need to actually create the graph and add the nodes and edges. So here I am just simply from the node and edge data we already loaded in. I'm just creating a graph in Network X format. So that is what is going on here. And then here's what our graph looks like. So each bubble is a node. As you can see, nodes can either be customers, car IDs, or pets. And then the edges between them are the relationships. So customer 5 points to customer 3 because customer 5 is friends with customer 3. Customer 3 points to car ID 10 because customer 3 owns car ID 10. And then customer 3 points to pet 2 because customer 3 owns pet 2. So our edges are our relationships between the nodes, and then the nodes are either customers, cars, or people. I mean, customers, cars, or pets. Great. Now let's get into the PyReason of it all. Let's add some rules and facts. Well, first we need to initialize PyReason. So we're going to load our graph into PyReason with the load graph function, and then we're going to make sure to set our settings.verbose to true and settings.atom_trace to true so we can keep track of our atoms. Great. So next, let's talk about rules in PyReason. So in PyReason, rules are used to create or modify predicate bounds associated with nodes or edges in the graph if the conditions in the rule body are met. So to the left of the arrow is what is called the head of the rule, and this is what's bounds will get modified if all of the body or everything to the right of the rule is satisfied. So the default in PyReason is the default bound is 0, 1, which is like the inconsistent predicate. And then if every clause in the body of the rule is satisfied, then the bounds will get annotated to 1, 1, or you can even customize how you want to annotate the bounds if all of the conditions in the rule body are met. But let's look at this through some examples given our graph. So the first rule that we're creating is the popular pet rule. So this means that a customer is popular if he is friends with a popular customer. So popular is the head of the rule, and X is the current customer, and customer X will be annotated to bounds will be annotated to 1, 1 or true for popular if customer X is friends with customer Y and customer Y with a customer Y and customer Y is popular. And then it's named the popular pet rule because the popular rule might be redundant because we already have assigning people popular. But this will make a customer popular. Next, our second rule is a customer has a cool car if he owns a car and the type of car is car 4. So again, the head of the rule is cool car X. So our customer X will be considered having a cool car if customer X owns a car and that car is of type 4. And then our cool pet rule is the exact same idea, just with pets, not cars. So a customer has a cool pet if they own a pet and the pet is of type pet 2. So again, the head of our rule is cool pet X, customer X. And then this customer will have a cool pet, or the bounds will be annotated to true, 1, 1, if the customer owns a pet and that pet is pet 2. And then finally, we have our trendy rules. This is a customer is trendy if he has a cool car and a cool pet. So that means that he has, in this specific example, car 4 and pet 2. So those are some rules on nodes in PyReason, but you can also add rules on edges or relationships. So we're going to add this rule that applies to the edges, which is two customers are car friends if they are friends and they own the same car. And so that will annotate that relationship. We'll annotate those bounds to being 1, 1 if two friends have the same car. Great. Now let's talk about facts. So you can think of facts in PyReason as kind of initial conditions or information that is a statement that you can be used to store information in the graph. So a basic unit of knowledge that can be used to derive new information. And so in this case particularly, it really is an initial condition because our only fact we're adding for this example is that customer 0 is popular from time step 0 to 3. So then we're going to assign customer 0 to being popular from our time step 0 and then ending at 3. And then this is called the popular fact. So this, in essence, we need to do because if you recall this rule for our popular rule, a customer is only popular if he is friends with a popular customer. If we, at the beginning, we don't have any customers that are assigned popular yet. So no customer would ever be popular because we don't have any other popular customers in our graph yet. So we are going to assign popularity to customer 0 for the duration of our time steps. All right, and then finally, now that we've added all these rules and facts, how do we run PyReason? We're going to run the function pr.reason over our time steps 3. In PyReason, you can customize how many time steps you want to use for this specific example. It's still pretty simple, so we're only going to use 3 time steps. But as your examples get more and more complex, as you add more rules and facts that might fire at different times, you can increase the number of time steps used to fully complete your reasoning process. So let's take a look at some code. All right. So here is our code file. Again, this will be linked in the description. We want to make sure we have PyReason imported and downloaded, and then also network X for our graph. Then again, we're adding in the node data here. We're adding in the edge data, and then we're actually creating the network X graph, and then we load it here. We initialize PyReason, and then here's where we add our logical rules, and then our logical fact, and then we are going to run our interpretation. And so this pr.reason is where the actual PyReason reasoning happens. And so after you've run it, the next step is you want to get the output. You want to see what happens, see what bounds have been annotated and changed. And you are going to do that by tracing the explainable output. So PyReason 3 has a few new functions which make reading PyReason's output even simpler and super explainable. So The first of which I'm going to talk about is our get and save rule trace function. So this function saves the rule trace for nodes and edges in the form of a CSV file. And the columns are time, so the current time step, the fixed point operation, so where the reasoning stabilizes, the edge or node that has changed if applicable, the label, so the predicate or ahead of the rule, the bound before and after the reasoning step, what the change in the step was due to. So this will either be a fact or a rule, and then clause 1, 2, 3, 4, etc. So what grounded the clause in the rule. All right, if we run our full PyReason file, as you can see, our PR save rule trace is down here. So we want to make sure that that's included. And if you click run on your PyReason file or however you run a Python file, then you should see two .csv files pop up, one for nodes and one for edges. So let's look at the one for nodes first. So as you can see, the first column, we have our time step. So at time step 0, we see that customer 0 becomes labeled as popular, which changes its bounds from 0, 1 to 1, 1, 0, 1 being the default bound, 1, 1 being the true bound. This is due to our popular fact. And then we also see at time step 1, this is the only thing that happens in time step 0. We also see in time step 1 that customer 0 is again still popular because of the popular fact. But now in time step 1, we start to see other things happen. So customer 4 becomes labeled as popular, changing its bounds to 0 from 0, 1 to 1, 1 because of this popular pet rule. And this is because customer 0 is friends with customer 4 is friends with customer 0. The same is true for customer 6. Customer 6 is friends with customer 0, so it becomes labeled as popular. Now, customer 4 also gets labeled as having a cool car, which again changes the bounds from 0, 1. All of the default bounds are 0, 1. And in this example, if the rule successfully fires and all the clauses in the body are satisfied, the bounds will always get annotated to 1, 1 or true. And this is because of the cool car rule, because customer 4 has car 4, which is the cool car. Same for customer 6. Customer 6 also has car 4, which is also a cool car. And then customer 3 is a cool pet, which if we recall is a very similar rule. This is a cool pet rule because customer 3 has pet 2, and pet 2 is a cool pet. And then customer 4 also has pet 2. So customer 4 has a cool pet and a cool car, which if we remember means that customer 4 is trendy because of the trendy rule that states that someone is trendy if they have a cool car and a cool pet. So those are all the changes that happened at time step 1. Now let's look at time step 2. So a lot is the same. Customer 0 is still popular. Customer 4 and 6 are still popular. But what changes here is customer 3 is now popular. And this is because if we look in the popular pet rule, now the list of popular customers, instead of just being customer 0 from our fact, has expanded to be customer 0, 4, and 6 because of the reasoning that happened in time step 1. This is why having multiple time steps is essential, because otherwise customer 3 would not have been labeled as popular because during the first time step, only customers friends with customer 0 would be labeled as popular. But now this group of popular customers can grow through friends of friends. So customer 3 is friends with customer 4 and therefore is now labeled as popular. And the same is true of customer 5. Customer 5 is labeled as popular because customer 5 is friends with customer 6. So again, customer 5 is not friends with customer 0, but because by time step 2, customer 6 is popular, and customer 5 is friends with customer 6. Now customer 5 is popular. And then these rules don't change. We don't change anyone's car or pet during the reasoning process. So customer 4 and 6 have cool cars. Customers 3 and 4 have cool pets, and therefore customer 4 is still trendy. And then the final thing that I wanted to show here, all of the same customers that are popular remain popular. But I wanted to show that now the list of popular customers has expanded yet again to have customer 0, 4, 6, 3, and 5. 3 and 5 joining from time step 2. And now that it's time step 3, they are a part of the popular customer list. And then the rest of the CSV file is the same as the first two time steps. So that is how you read one of these get rule trace for nodes. Now let's look at the edges. It's going to be much shorter. Much shorter. So if we remember, our only edge rule was our car friend rule. So if two customers are friends and they have the same car, then they will satisfy the car rule. And again, their bounds will get changed from the bounds of the head of the rule will get changed from 0, 1 to 1, 1. And they will be labeled, this edge will be labeled as car friend. So this rule only satisfied with customer 3 and customer 1 because customer 3 has car 0 and customer 1 has car 0. So this doesn't change for any of the time steps because no one's car changes. So this makes sense. And yeah, customer 3 and customer 1 are the only two nodes that satisfy our car friend rule, being friends and having the same car. So this is what the CSV file looks like for edges. Great. So now let's head back to our slideshow. We have a couple other ways that you can look at PyReason output. The first is the get.getDict functions. This is the get interpretation dictionary. This stores the output in a triply nested dictionary, the most outer loop being time, then graph component, then predicate bound pair. So let's look at if we run this on our function. So as you can see here, we have interpretations equals interpretations.getDict, and then we are going to use pprint for nicer formatting. And once you again run your Python file, it should show up in the terminal after a minute or so. And here you can see we have our nice triply nested dictionary. Let's get all the way up to time step 0. All right. So we have time step 0, and then we have the graph components. So we have all the car nodes, the pet nodes, customer nodes. And then you can see if those nodes or edges have any rule or fact annotations on them, then those will pop up here as well. So remember, customer 0 is popular. So that shows up. And then at time step 0, the edge between customer 3 and customer 1 is labeled as car friend 1, 1. So that shows up in time step 0. And then in time step 1, this is where customer 3 gets labeled as a cool pet. Customer 4 gets labeled as having a cool car, cool pet, being popular and trendy, which we should remember from our rule trace nodes CSV. This right here. All this information is the same. It's just changing how it's formatted. So I suggest that you look at all of this when you're running your PyReason functions, or if you have certain ways of looking at information that make way more sense to you, then lean into that. But I want to emphasize that these are expressing the same information just in a different format. And then customer 6 again is popular and has a cool car, but we know this. And then again, customer 3 and customer 1 are car friends. And then in time step 2, now if we remember, customer 3 is popular and customer 5 is popular because they were friends with customer 4 and customer 5. The triply nested loop doesn't give quite as much background information as the CSV file does, but it might be easier for you to read, or you might not need to know exactly what factor rule or grounded clause changed the bounds. You might just want to know what bounds are changing. So yeah, and then for time step 3, everything is going to be the exact same as time step 2 with no new changes. So that is how you read the interpretations.getDict function. And then we have one other function that is also new to PyReason 3, and it is our filter and sort nodes or filter and sort edges. So this function filters and sorts the node changes in the interpretation and returns a list of pandas data frames that contain the filtered and sorted interpretations. So let's run filter and sort nodes on trendy, cool car, cool pet, and popular, which are the 4 rules that we used in our reasoning for nodes. So as you can see, here's our pandas data frame. Let me show you where I run it in the code. All right, data frame one, filter and sort nodes, and then I print it out with this little for loop. I think it makes it a little bit more readable. So we can see at time step 0, the only node change is customer 0 becomes popular. And then at time step 1, the node changes is that customer 4 is trendy, has a cool car, cool pet, popular. Customer 3 has a cool pet. Customer 6 has a cool car and is popular. And again, this is all the same information as the pass, as the getDict and the CSV file, just in another different format. We can see in time steps 2, now customer 3 and customer 5 are popular where they weren't popular before. And customer 5 wasn't even included because none of customer 5's nodes had predicate bounds that changed. So this also is nice because it filters it. It only includes the nodes which have bounds that change. Um, yeah. And then again, customer 3, we know nothing changes in the nodes. For time step 3, everything is stable after 2. Great. And then I have one final function to walk through you guys. Almost exactly alike to filter and sort nodes. I have filter and sort edges, which filters and sorts the edges. The edge changes in the interpretation and returns a list of pandas data frames again. And so this time we're going to filter and sort our edges off the car friend rule. And again, let's show where this is in the code. So right below, I have data frame 2, which filters and sorts edges on car friend. So it will only show edges that were altered by the car friend rule. And then here is my printing of data frame 2. And then again, if I run my Python file and scroll to the bottom, you can see that for time step 0, 1, 2, 3, same as we saw in the dictionary and the edge trace CSV file. Customer 3 and customer 1 are the only edge that gets labeled as car friend. And this happens from time step 0 through time step 3. But this is a filtering and sorting of the edge changes in the interpretation. Great. All right. Well, I hope you guys enjoyed this tutorial. Again, the full link to the code will be in the description below, as well as the link to the GitHub, which has documentation and much more information about PyReason, how it works, and how you can use it. And please comment any questions, suggestions, feedback below. And yeah, have a wonderful rest of your day. Thanks. Take care.